repeat, if there's an activator and a deactivator on it, then the activator wins.
As far as the directing effects are concerned. That's right. If you're trying to predict the directing effects, you should focus on the activators more than the deactivators. That's right. Let's predict the major product or major products here. Looks like you guys got this right. Is it going to be easy or hard to add the second bromine?
Hard.
Hard, because we've memorized that these are deactivators. Not very hard, but somewhat hard. So we certainly need a catalyst here. And then this is an O and P director. Why is it an O and P director? Because we just memorized that. We're just memorizing things for halogens. So here's the ortho position and here's the para position. Now, if they ask you for the major products, you would want to draw both of these. However, which of these do you think we might get a little more of?
Para, because it's less sterically hindered.
That's right. In fact, now there are some exceptions to that, but usually you get more para than ortho because of steric hindrance. You can see that in the ortho position there's more steric hindrance between the substituents, and here there's a lot less steric hindrance. Now actually, according to the book, in this case the para gets 85%. And the ortho only gets 13%. So there's a pretty big asymmetry here. Even though if they ask you for the major products, you'd still want to draw both of these. I guess that's because bromine is quite big. Bromine is a pretty big atom, so steric hindrance might be a pretty big
issue.
Is
the other tiny little percent a meta?
That's right. There's only 2% meta, so that's certainly pretty insignificant over here.
So if they ask you for the major products, then you put both of them. If they ask for the major product, you put the para.
Yeah, although I don't know if they would actually, that would be a little too subtle.
Usually they say like put the major product in parentheses and S.
Then I would draw both.
Both.
And then what I think they would do is they would say something like, of your major products, which would you get more of? They would be explicit, otherwise it wouldn't be fair.
Okay.
Or they would specifically say, of the two things you drew, which would you get more of? So usually we would expect more para than ortho. But nevertheless, we generally draw both. Both the ortho and para are important. So ortho-para directors usually direct more para than ortho, but we usually want to draw both of those. If we try to add a third substituent, where would the third substituent go here?
On the OHCH3.
On the ortho of the CH3, because it's less sterically hindered than the ortho of the OH.
Let's see. Actually, this might be more sterically hindered. I don't know which one's more sterically hindered. They're both about the same in size. So this
I would
is
say the OH, isn't it? Because that one's more electron donating than the CH3, so that's going to be the more stronger activator.
Guideline number 1, the most powerful activator controls the position of attack. The more powerful activator, so it turns out that steric hindrance is not the crucial issue here. The more powerful activator controls the position. Well, who's more powerful here?
OH.
That's kind of indicated by our table, right? That's why I put the oxygens up here and the alkyl groups down here. Remember, the alkyl groups just have that hyperconjugation effect. That's not going to be as strong as resonance. So where would we put the new substituent? Here. The major attack of the new substituent would be here. So what have we done so far? We've talked about how to add, well, in chapter 15, we talked about how to add the first substituent to benzene. And so far today, we've talked about how to add the second substituent to benzene. but we should spend a few minutes talking about adding a third substituent to benzene. What happens if you've already got two substituents on there? Who determines the directing effects? Well, guideline number one, the more powerful activator controls the directing effects. That's why we had to know roughly who was more powerful and less powerful in our table here. So here we want to choose the ortho position based on this more powerful activator, not this less powerful activator. Where would we add a third substituent here?
The ortho of the CH3, because activators beat deactivators.
That's right. If the more powerful activator wins, there's no contest here because this isn't an activator in the first place. This nitro isn't even an activator, so we should base this on the activator. We should be ortho to the activator, which puts us in the O position.
What happens if the deactivator isn't para to the CH3? Like, what if it's meta?
Yeah, we should be looking at an example of that pretty soon. Well, I don't think that it makes much difference. Remember that if there's an activator and a deactivator, we should just base things. Oh, that actually is a good point. So
yeah, like wouldn't you get the ortho and the para that's not between the two?
That's actually a good point. Yeah. So now there's two ortho positions, here and here. But which of these ortho positions is better? The one on the left. Now steric hindrance plays a big role. Basically, a position that is between two substituents should be considered very hindered. A position that is between two substituents should be considered very hindered. So there's not going to be much attack in this position because there's steric hindrance on both the left and the right. So we would expect a new substituent to come in here, or maybe down here. These seem like two good places to put the next substituent, because this is the ortho position for the alkyl group, and this is the para position for the alkyl group. And neither of these has too much steric hindrance. But this position has way too much steric hindrance. There's not going to be a lot of important products over here.
Are we supposed to know which one's going to be better, the para or the...
I don't think so.
Okay.
Maybe this has more steric hindrance because the NO2 group is bigger than the methyl, but that's a close call. I don't know if that would really get into that.
Cool.
Where would the third substituent add here?
Ortho
to the CH3 bottom one.
So, on the top or on the bottom? Actually on the top.
Yeah,
Isn't that one more intimidating because it's...
Now, I guess in a sense, maybe you would think this is more electron donating because there's more electrons, but it turns out that there's huge steric hindrance here. This is what we call a trig-butyl group, right? When we really want to put in a lot of steric hindrance, we put in a trig-butyl group. So because of the huge steric hindrance here, that's going to outweigh any additional electron donating ability this has. So the steric hindrance would win out here, so that we could attack here. This position is equivalent, so we could attack at either of these two top carbons. So this is subtle. Sometimes steric hindrance does play a role here. Where should we attack here?
Sterics wise, should go next to the CH3.
On the left or the right? Why not here?
Because it's too...
Yeah. We don't generally put a substituent directly between two other substituents. That's too much steric hindrance. Any other good positions?
It could be the para of the CH3, but isn't that
Yeah.
too close to the Cl?
I think both of these would be worth drawing. After all, this is close to the alkyl group. This doesn't have any more steric hindrance than this does over
It's
here.
like the NO2 one that we just did, right?
Yeah, this is actually very similar to the one we just did a couple seconds ago. So I would draw both products. One product where the other, so I'm not trying to say you would get both attacks here. Maybe what the book does is they just draw arrows. So we could get an attack here, or we could get an attack here. That's very similar to an example we just did. But we wouldn't worry about the attack here because of steric hindrance. And of course, we're focusing on the directing effects from the alkyl group because it's the activator. this is a deactivator, so it's not going to have important directing effects. Remember that if there's a competition between activators and deactivators, the activator controls the directing effects. So we're focusing on the activator here.